at our first example. So we're starting off slow, starting off easy, just sort of recapping what we spoke about on Wednesday, also because I feel like it's been a very long time since I last saw you guys. So just starting with something easy, and then we're going to build it up. So we want to find the value of the following, but importantly, without the use of a calculator. So whenever we see that, we should be thinking special angles. Now, your special angles, there are a few of them that you need to know. It's your 30, 60, 45. It's also then your axes on your Cartesian plane, so 0, 90, 270, 180, 360. Those are essentially the special angles that you need to know. The triangles that we've drawn are for 30, 60, and 45. When seeing this, immediately you should be thinking, how am I going to go from an angle of 75 degrees to one of those special angles? Because it's without a calculator, that's the only way we can do it without a calculator. Now, if we have a look at this, and obviously just because, you know, I was overconfident in what was going on here. Okay. If we now compare this to our double angle formulas that we know, and move this, make it smaller. Hopefully you'll agree with me that the expression that we've been given looks very similar, or is our sine double angle identity. So if we compare these two, we've got 2 sine A cos A, and we've got 2 sine 75, and then cos of the exact same angle. What that means is obviously I'm going to apply my sine double angle formula. So it's sine of a double angle of 75 degrees, which gives me sine 150. Right, now remember, we want a special angle. This is not yet a special angle. Because, however, it is an obtuse angle, we should be thinking about, can I apply a reduction formula? And in this case, I can, and that reduction formula will contain the special angle that I want. Because 100 minus 30 gives me the 150. This reduces down, and if you think about your cast diagram, 180 minus is quadrant 2. That's where cos is positive, so this reduces just to sine of 30 degrees. And sine of 30 is a half. Whoops. So that's essentially what we need to start thinking about when we're approaching expressions that we need to simplify, expressions that we need to find values of, etc., etc. You need to, and you're going to see as we go along, I'm going to say this quite often, you need to be thinking of the formulae that you know. You need to be thinking about how you can manipulate an expression to get what you want. So to get the double angle that you want, to break it up into a compound formula, to prove the identity, whatever the case is. How can you use manipulation to get what you want? It sounds very toxic, this whole trig idea, but trig is manipulation. You also need to start thinking very critically about the numbers that you're working with. It's going to become a bit more important in our next example. When I say thinking critically, you need to start thinking about the relationships between the angles that you've been given, or the values that you've been given. Excuse me. So can this angle become a double angle? Does this angle relate to this other angle through a double angle, through a compound angle, what? Is there a way for me to find a link between the angles I've been given? And like I say, as we look at example 2, that's going to become a bit more important. But these are the skills you need to start developing, and you will start developing as you do past papers, as we go through these examples. All right, but take a screenshot of this first one. Like I say, we're starting off easy, but as of our next example, we're getting into the nitty-gritty, well, the nitty-gritties, the more complex type of questions where we do need to think a little harder. Remember, grade 12s, if you have a question, feel free to unmute, feel free to put on the chat, but please ask as we go along, because this is trig. I know it's not easy for everyone. You need to ask the questions as we go. Okay. So if we look at example 2, excuse me, our first example here, it looks pretty similar to what we just did. However, the difference is that those angles are different. So yes, in the back of my mind, I'm thinking, cool, this is a sine double angle. The problem is, though, that those angles are not the same. For me to apply the double angle formula, remember, angles must be the same. So now the question is, remember I said, how can we manipulate our expression to get what we want? We kind of can see that I'm going to have to get a double angle. So how can I manipulate the situation to get those angles to be the same? Now, if you look at both of those angles, they're both bigger than 90. So one is an obtuse angle, one's a reflex angle. Either way, they're not acute angles. I've been saying this since our first lesson. If it's not an acute angle and you're trying to simplify an expression or find the value of an expression, use reduction. Okay, reduction formulae introduce acute angles to your expression, and hopefully the goal is going to be that when I apply my reduction, it reduces to a common acute angle that I can now apply my double angle formula to. So we're going to start there. So if I apply a reduction to sine 105, it would be 180 minus 75 degrees. And to cos 275, that would be cos of 180 plus 75 degrees. Now this is great. Okay, because what I see is that through my reduction, my angles are now going to be the same. And that will allow me to apply my double angle formula once I've sorted out my reduction. So remember your cos diagram, 180 minus quadrant 2, sine is positive. So this is just 2 sine 75 degrees. 180 plus is quadrant 3, only tan is positive there. So this means I've got times negative cos 75 degrees. Sorry, 70. Didn't get better. 75 degrees. You get what I'm saying. If we just sort out that negative, it's actually a negative 2 sine 75 cos 75. This now looks like my double angle formula. So just remember, sine of a double angle is 2 sine A cos A. That's exactly what I have here. Obviously, except for the negative, but that's just a coefficient. We're not stressed about that. So what this means is that this actually becomes negative sine of the double angle of 75 degrees. Because remember, this 2 sine 75 cos 75 is my double angle formula. Let's actually do this. Like I said, that negative is just a coefficient. So we leave it there as a -1. We're just going to times our answer by -1. Now, we've already done the second part, so I'm not going to re-explain it. You apply your reduction 30 degrees. You are more than welcome. So double 75 is 150. You apply your reduction and you get 30 degrees. You are more than welcome to not show the 180 minus 30. That's not necessary to show. Obviously, by all means, show it if you want to, but you don't have to. You can go straight to the simplified reduction. We already know that sine 30 is a half, so this simplifies to negative a half. So this question was not difficult at all. Shows us the need to often, and honestly most of the time, manipulate expressions. You're going to manipulate through the knowledge that you already have. Identify what it is that you're working with. So here I could say I'm probably working with the sine double angle based on what I was given. I could see that I needed to apply a reduction formula in order to get that acute angle that would match up for my double angle, and then apply the knowledge that you already have. So again, trig manipulation. That's really all that you're doing. I can't give you exact steps to follow because it's very much dependent on the question. But if you can start thinking critically about what do I have, what do I want, what tools do I have available to me, you're going to hopefully become more comfortable with it. Again, guys, ask questions as I go along, please. All right, so let's take a quick screenshot, and then we're going to have a look at a slightly more complex question that we need to deal with. Okay, so remember all of these, I didn't write an instruction here, is determine the value of the following without the use of calculator. It's the same instruction as example 1. I just forgot to put it there. Okay, so let's have a look at B. So B, we've got sine 35 cos 35. divided by tan 225 cos 200. So before you start anything, look at what you have, look at what you might be able to do. So the sine 35 cos 35, that to me is reminiscent of the sine double angle. I'm missing the 2 because remember the sine double angle is 2 sine 35 cos 35. So that's a problem. But somewhere at the back of my mind, sine double angle might come into play. That's the first thing. Second thing that I notice in my denominator is neither of those angles are acute angles. So I'm going to have to apply a reduction in order to get acute angles. You might not see the third thing immediately, but the third thing is that aside from the cos 35 and sine 35, none of these angles are matching up. None of these angles are showing a double angle relationship or are able to simplify to only 35 degrees that we can divide. So that's a bit of a problem. So we're going to have to think about how we can deal with that. Right, but first things first, and I've said this all the time, first things first, change your non-acute angles to acute angles using reduction formulae. So right now I'm going to leave my numerator exactly as it is, because I don't actually have an issue with it at this point in time. I might need to change it later, and that's later's problem, but for now I've got no problem. Tan, I'm going to reduce this by saying 180 plus 45. And remember, 45 is a special angle. Because I'm determining the value of the following without the use of a calculator, I should also have special angles in the back of my mind. Now, cos 200, unfortunately, there's no way for me to get a special angle. So I'm just going to reduce it to acute angle by saying 180 plus 20. We'll chat about why this is useful in a second. Right now, that's the only thing I can do to get it to an acute angle. Okay, so my numerator is going to stay as it is. Like I say, I can deal with it later if I have to deal with it. 180 plus for tan, quadrant 3, tan is positive. So this just reduces to tan 45. That's a special angle of 1. So if you wanted to go straight to 1, that's also absolutely fine. Cos 180 plus, quadrant 3, so it's a negative cos 20 degrees. So in reality, I just have my numerator, and in my denominator, I'm actually just working with a negative cos 20. Okay. So now I'm a bit stuck because, like I said, my angles don't match up. So it's not like I can just divide away the causes. Can't do that because the angles aren't the same. None of those are special angles. So I have a bit of a conundrum. What I now need to think about is, what is the next way I can manipulate my angles? Remember, I always say to you, avoid co-ratios where possible, but sometimes you just have to use a co-ratio. So let's think about the co-ratio you would potentially use, let's say on the 35s. The co-ratios we are generally focused on are the 90 pluses or minuses. Now you would have to say 90 plus 55 or 90, in this case, 5 in the co-ratio. Now 55 still doesn't help me because all I'm doing is changing this to an angle that I don't want. So if I go to my denominator, the co-ratio I could use here is 90 minus 70. 90 minus 70 is 20. And already a little alarm bell should be going off because 70 and 35 have a relationship. It's actually a double angle. Okay, so if I think critically about my numbers that I have, if I apply a co-ratio of cos 90 minus 70 here, that 70 is a double angle. Because if you were to go and say 35 degrees times 2, you get 70. That now links to my 35 in my numerator. So again, you need to start thinking about the relationships between the values that you have. So that's exactly what I'm going to do. I'm going to apply my co-ratio. Okay, so again, leave the negative there. It's just a coefficient. We'll deal with it when we need to deal with it. This becomes cos 90 minus 70. Remember, co-ratios mean there's a name change. 90 minus, it's just a name change, not a sign change as well. So numerator is still the same, but this is now just negative sine 70 degrees. And this is now where the double angle comes in. Because we've got the 70, we can apply our double angle formula to sine. And remember I said right at the start that sine 35 cos 35 kind of looks like a double angle, it's just missing the coefficient of 2. We can see that now. And because it kind of looked like the double angle, and because we're going to apply it now, things are going to cancel. Okay, so in applying my, excuse me, I'm applying my double angle, my denominator, I've got minus 2 sine 35 times cos 35. And obviously my numerator hasn't changed, so that is still sine 35 cos 35. Okay, and like I said, things can now start dividing away. So cos 35 divided by cos 35 is 1. Sine 35 divided by sine 35 is 1. And so what we're actually left with here as a simplified value is negative 1 over 2, or negative a half. So guys, when it comes to questions like this, like I say, there's certain things that you can definitely start with. Your reductions, your special angles, if you can apply them immediately like we did with the tan. Those are things you can start to do immediately. The skill comes in you being able to look at the values that you're working with and figure out their relationship. This was a little harder because you first had to get to the co-ratio to then see the double angle. But these are also things that you can think a little bit ahead about. This is where I'm at. If I did this, remember I said, if we apply a co-ratio, what do we end up with? Is there now a relationship? These are obviously things that you get better at with time. It's not something that you can just do straight off the bat unless you're someone that really enjoys trig and this comes easy to you. That's awesome. It unfortunately doesn't come easy to a lot of people, and so this just comes to practice. Okay, but like I said, there are certain things you can definitely do to start off with to help yourself get there. Okay, so let's take a screenshot of this, and then we're going to have a look at a slightly different one and how we deal with that. Okay. Right, so if we have a look at example 3, still a fraction, but we now have a situation where we are subtracting fractions. So guys, my question to you is, if you think back to our grade 8 and grade 9, what do we always need to find when we are adding or subtracting fractions? You can just pop it on the chat if you want. What do you have to find if you're going to add or subtract fractions? Anyone? Okay, that's fine. We have to find an LCD. Okay, LCD you have to have in order to add or subtract two fractions. If we now have a look at our situation, we obviously go back to what we started with. So like I say, all of these angles are acute angles. So that means I can't really apply a reduction. I could apply a co-ratio if I wanted to, but right now that's also not going to help me, because if I apply a co-ratio to 36, that would be 90 minus 54. Doesn't match up with 12. If I applied it to the 12, it would be 90 minus 78. Doesn't match up. Okay, so I've got a bit of a problem in that I can't apply a reduction or a co-ratio. Because I'm subtracting fractions, I know I can definitely find an LCD. So that's what I'm going to do. If I have a look at this, my first fraction is missing, rather, remember your LCD, you take each unique factor of your denominators, and that becomes your LCD. So this would be sine 12, cos 12. So this is missing a cos 12. Remember what you multiply in your denominator, you multiply your numerator, and this is going to be sine 12. Same thing, what you do to the bottom, you do to the top. Okay, so now everything's one fraction over sine 12, cos 12. Your numerator is sine 36. Oh gosh, okay, so it's not going to work there. We'll move it. Numerator is sine 36 cos 12 minus cos 36 sine 12 all over that LCD, like I said. And what you should now sort of have an alarm bell going off of is this numerator. This looks very familiar. It's a sine cos minus cos sine. So if we just jump back up to here, it's a compound angle. Okay, we go and put it next to here so that we can compare. Okay, let's try that again. Right, so if we go and compare the situation that we have with our compound angle formulae, we've got a sine cos minus cos sine. Sine cos minus cos sine is a compound angle formula for sine of A minus B. So that means I can apply my compound angle formula there. Right, so let's do that. Again, we haven't done all of this work to just stop here. We now can start applying the things that we can apply. So in my numerator, this becomes sine 36 minus 12. And my denominator is obviously sine 12 times cos 12. Right, 36 minus 12, 24. So I've got sine 24 over sine 12 cos 12. And hopefully what you notice is that 24 is double 12. So you've got a double angle. Double angle for sine is just a 2 sine A cos A, sort of what we've already been doing. So 2 sine 12 cos 12 over sine 12 cos 12. And what you can now hopefully see is that things divide away. Cos divided by cos, sine divided by sine. And so actually all you're left with is 2. Okay, so when you have a situation like this, if you can't apply the reduction with co-ratios, think back to your algebra, because remember I've also said to you trig and algebra are very closely linked. You're applying all the same skills. So think back to your algebra. Is there anything that you can do in this case? Because it was the subtraction of fractions, I could find an LCD and I could go from there. Okay, guys, so take a screenshot of this one. And then there's 2 that you're going to try. I'm hoping that we are still here and focused. Okay, so you're going to give these 2 here a try. I'm going to give you 5 minutes and then we'll have a look at the answer. Remember, if you've got questions, please ask. You can put it on the chat, you can unmute, you can send me a message, whatever you want to do. Let's try these 2. Well done, Daniel. Put up the answer in a minute. Back yourself though. Ah, cool. Right. Let's have a see. Okay, so the first one, very similar to the first question that we did. Two acute angles in my numerator, so I'm not going to touch those to start off with. But obviously I can apply my reduction in the denominator. What that means is I get an angle of 80 degrees, which then links with my numerator because it's a double angle. So I apply that double angle identity or formula rather, and I'm able to simplify because everything essentially cancels. So again, looking at the relationship between your values, really, really important. Okay, so that's the first one. The second one, I will make this a bit smaller so you can screenshot everything. The second one, let's actually do this. Oh, I didn't think of this before. Right, second one, you had the tan 135, if I remember correctly, plus 2 cos squared 15. Now, guys, already that 2 cos squared 15, and a little bell should be going off because that is reminiscent of a cos double angle. Remember, one of the cos double angle formulas is 2 cos squared theta minus 1. So yeah, we're missing the minus 1, but that's fine. We can deal with it if we need to deal with it. But somewhere you should be thinking double angles. So again, deal with the angle that's not acute. That's the 135. Apply your reduction, and you actually end up with negative tan 45. Now, tan 45 is a special angle, and it becomes 1. So there's that negative 1 that you were missing from your double angle identity. So remember, double angle identity, or one of them, for cos 2a is 2 cos squared theta a minus 1. So now we actually have both of those terms. There's the 2 cos squared, there's a minus 1. You can just swap them. There's nothing wrong with rearranging terms as long as you keep their signs correct. Do it. That's then the double angle. You should also be thinking double angle because it would say without a calculator, 15, if you double that, it's 30, that's a special angle. And so we are able to double the angle to get cos 30. Cos 30, root 3 over 2. Okay, so when looking at these, like I say, it's really important to start looking at the relationships between the values that you have and how can you manipulate your expression, your equation, whatever you're given to get what you want, essentially. Like I say, trig is toxic. Manipulation is the key word of the day. Okay, you guys can screenshot that, and then we're going to have a look at another example. We are going to do a whole lesson on identities, but I thought I'd throw one in because why not? And looking at how we can now use our double compound angle formula to start proving identities. Okay. Okay. So we have got prove the following identity of sine 2 theta times tan theta divided by cos 2 theta plus 1 equals tan squared theta. Lots going on. Firstly, remember that when you prove an identity, you don't work with it as an equation. You pick one side to work with, either your left-hand side or your right-hand side. Essentially, what you're trying to prove is that it is actually equal. So you cannot work with it as an equation because then you're assuming that it's equal. So you pick a side to work with. That leads me to the second thing of what side do you pick? So generally speaking, we try and pick the side that's more complex, i.e. the side that we can manipulate more. So we're looking out for tans, we're looking out for double angles, we're looking out for potential reductions that we can do. Those are all the things that we look out for. Now, in this case, there's a tan on both sides, but pick the more complex side. Pick the side that you can do more with. So yeah, we've got a tan squared theta on the right, but on the left-hand side, I have a tan, I've got a sine double angle, and I've got a cos double angle. So because I've got more that I can deal with on the left, that's the side I'm going to work with and that I'm going to manipulate. All right, so I'm going to work with the left-hand side. You always just state which side you're going to work with and you're going to manipulate, and then you can just ignore the right. Okay, you can make your final statement at the end, the left is equal to the right or it's not, but you say what you're working with and then you can go from there. Right, so we've got, okay, doesn't enjoy me, so that's fine. But our left-hand side, and that's the sine 2 theta times tan theta over cos 2 theta plus 1. Okay. First things first, always change the tan. So one identity that we should sort of know already from grade 10, change the tan. Tan identity is that tan theta is equal to sine theta over cos theta. And what I want you guys to just remember is that this can be, well, there's multiple forms of this identity. So this could also translate to a double angle. So tan 2 theta is equal to sine 2 theta over cos 2 theta. It could also translate to a squared. So tan squared theta is equal to sine squared theta over cos squared theta. Those are all forms of the tan identity. So it doesn't have to be tan theta. It could be tan 2 theta. It could be tan squared theta. They're all forms of that identity. It's going to be helpful later on. So that's the first thing I'm going to do. The second thing that I'm automatically going to do, because sine of a double angle only has one formulae, I can change it immediately. So sine double angle is 2 sine theta cos theta times, I'm changing tan to sine theta over cos theta. For now, I'm going to leave my denominator. Now, the reason I'm going to leave my denominator is because, remember, cos of a double angle has 3 options. We've got cos squared A minus sine squared A, not to be confused with your square or Pythagorean identity. We've got 2 cos squared A minus 1, and we've got 1 minus 2 sine squared A. Help if I use some A. Okay, so those are the 3 forms, or the 3 formulas that go with your cos double angle. We are going to need to decide which one we're going to work with. And before I make that decision, what I want to do is I want to simplify what I've just done in my numerator so that I can kind of figure out which is going to be most beneficial for me. So when I do go and simplify this numerator, remember what you've got is the 2 sine theta cos theta times sine over cos. So you now have a cos in your numerator and a cos in the denominator, which actually divide away. And so what you have in your numerator is 2 sine squared theta, because sine times sine, sine squared, all over cos 2 theta plus 1. Okay, so now I need to decide what double angle for cos do I want to work with. If you go back to where we started, remember what we're trying to prove is that that whole left-hand side is equal to tan squared theta. This needs to take you to what I said over here. The fact that tan squared theta could actually be written as over cos squared theta. I already have a sine squared theta in my numerator. So if I can get a cos squared theta in my denominator, that gives me tan squared theta. And this is sort of how you need to approach identities. Start with the manipulation you know you can do. Once you've simplified and dealt with that, go back to what you're trying to prove. How are you now going to continue your manipulation to get where you want to be? You always need to be referring back to the side that you are trying to equate it to. So because I have that in my head, I know that I need to pick a double angle that contains cos squared. That would mean I've got 2 options. Option 1 is cos squared minus sine squared, or option 2 is 2 cos squared minus 1. If I chose the first one, I'm now introducing a sine squared. I don't want to now introduce something that's going to cause me more problems, because then I'm going to have to deal with the sine squared. So where possible, I'm going to try not introduce too many new trig ratios. The second option, I'm introducing the cos squared, and yes, I'm introducing a minus 1, but go back to what you have. In your denominator, you've got a plus 1. That's the additive inverse. Plus 1 minus 1, it's going to cancel away, leaving me with just that cos squared, which is what I want. So I'm going to go for option 2 in terms of my compound angle formulae. Sorry, it sounds like there's chaos happening outside. So the 2 sine squared theta I'm happy with. This cos 2 theta, I'm now going to change to 2 cos squared theta minus 1, that's the identity, and then I still have that plus 1. Additive inverse, that's gone. So I just have the 2 sine squared theta divided by 2 cos squared theta. That's great, because what happens now? 2 divided by 2 is 1. And now I just have that sine squared over cos squared. Full circle back to that tan identity. And so what this actually simplifies to is tan squared theta. And so what I've established is that this identity is in fact true. The left-hand side is equal to my right-hand side. Okay. So when it comes to identities, like I said, they're not easy. I can't just say follows these 5 steps and you're going to be fine, because that's not how it works. You need to start with the manipulations that, I want to say you have no choice in, but there's only one option. Only one tan identity. Sine double angle, there's only one there's only one sine double angle formula. Start with those, because there's nothing else you can actually do. Then you can start to see, okay, this is where I'm at. Go back to what you need to prove, this tan squared theta in this case. How do I continue my manipulation? All right, sometimes you're going to get to a point and you're going to look at it and be like, I can't do anything more. And you need to go English. You're going to have to go back and think, okay, how could I have done this differently? That if you are always referring back to your original question, to what you're trying to prove, hopefully it will avoid you getting halfway through working out, realize you've messed up and needing to start again. So always just refer back to what you have. Okay, so take a screenshot and then you're going to try one by yourselves. Okay. Okay. Excuse me. So it's not quite a prove the identity, but you have been given an expression of 16 sine x times cos cubed x minus 8 sine x times cos x. And my instruction is write it as a single trig ratio. So you've got 2 terms there. I want you to write it as a single trig ratio. And quite honestly, I could make this a proof the following. So I could say, take the 16 sine blah, 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 equals this, prove the identity. So it's the same sort of logic. Look at what you have. Are there double angles you can use? Are there identities that you can use? I'll give you a little hint. Can you factorize? And then you go from there. Okay, so give it a try. Let's see what happens. And we'll have a look. I've given you a hint. My hint was factorize. So I'm going to say 3 minutes, and then we'll see where we're at. How are we doing, guys? Are we done? Do you need another minute or two? I'll give you 1 more minute. So I'm going to assume. Okay, cool. Thank you, Daniel. I'll give you another minute or two. Thanks to Tabo. I'm just going to give 1 more minute and then we'll have a look. Okay, guys, let's have a see. Right, so my hint was a factorize. So bear in mind, one of the things, and it doesn't come up often with identities, but one of the ways that we do prove an identity is through factorization. Like I said, it doesn't come up a lot. It's the same with general solution and equations. One of the ways we can sometimes solve an equation is through factorization. Not something asked often, but it is one of the ways. So always just bear in mind. I said earlier, always think back to your algebra knowledge. Part of algebra is factorization. So it has to come in or could potentially come in. Okay, so we factorize. If you go and have a look at what you were given, you have got a common factor here of 8 because 8 divides into 16 and 8, as well as a sine x in both. So there we go. And then 1 cos x in both of them. And so if you now go and take that out as your common factor, what you end up being left with is a double angle. So that can then, what's the word? Reduce, simplify to the cos double angle. And it means that you can now start applying the formulas that you know. Okay, the next thing, and we did an example like this, I want to say last week Wednesday. I'm pretty sure it was last week Wednesday. But I did an example with you guys where I said to you that this 8 sine x cos x is technically a sine double angle. If you take out a common factor of 4, that leaves you with that coefficient of 2 that allows you to apply the sine double angle. So remember, I said it's part of the manipulation that we expect you to be able to do. If your coefficient is greater than 2, but still a multiple of, you can take out a common factor as you need to in order to create that 2 sine cos to apply your double angle. So that's what we needed to do here. So because we had, So because we had the double angle, what we then ended up with was a situation where we had, sine 2x, cos 2x. So we had the same angles, which technically actually means you had another sine double angle. So again, if you factorize out a 2, you had a sine 2x, cos 2x. and that would then simplify to 2 sine 4x. So it's kind of one of those, it's not factorization obviously all the way through, but it's kind of one of those where you have like dots multiple times. We can keep applying our double angle until we simplified it to 1 sine double angle. And remember, that was our goal, to get it to a single trig ratio. So I reckon you guys probably at the very least got to the point where you had your 2 double angles. Perhaps applying the next set of double angles was a little trickier, but always just remember that as long as your coefficient is a multiple of 2 and you've got sine and cos of the same angle, you can just keep applying your double angles until you can't anymore.